Aha.
Erken heyecanlandık.
Erken heyecanlandık. Tamam, o zaman bir fıkra anlatalım. Ne bileyim, herkes geldi, zil çaldı, ben de geldim.
Evet, biri zil çaldı dışarı.
Ben çok seviyorum zil çalmayı. Bakayım burada. Çağırdım müşteri bakıyorum.
İstiyor musun?
Yok, yok. Yok, yeterince içtim.
Okay.
Okay.
Okay.
All right, so everyone, welcome to, I suppose, the last Nanocolloquium of the year. So today we are very happy to host an old friend and old colleague, Gökhan Ünel, from UC Irvine. So I met Gökhan when I was an undergraduate student at Boğaziçi University. He was doing his PhD at the time. We graduated at the same time. I finished my BS, he finished his PhD. And he's the first person I actually did research with. I had started in the lab he was working at, and I was completely interacting with him, so he was literally my first advisor. And and we also played Doom together on Friday evenings and ordered pizza into the lab and rode bicycles in the hallway.
He's polite saying that you're old.
No,
He's being polite.
No, I'm being polite, and I'm saying that as being a great mentor to me at in those years. And after that, he actually started working at CERN. I believe he has the title of the first person to work at CERN directly from out of Turkey, employed by CERN. And after that, he was in the US for a few years and back at CERN. And since 2003, I believe he's affiliated with the University of Irvine, but he's spending all of his time at CERN since then. So we asked him to give us a talk that is a little bit different than the general Nanocolloquium series here. This is really ultra nano, basically looking at what's really at the bottom, and I'm sure he'll do a terrific job with it. But our perspective is, we're looking at understanding what happens at the nanoscale and learning how to exert control on the individual atoms or groups of few atoms at the nanoscale. But there is something much deeper. There's something much, there's organization and there's structure at a much smaller scale. And we felt that having a perspective from that side, where nano is ultra large for them, they're dealing with 10 to the 6, 10 to the 9 times smaller spatial scales. That will give a very nice twist to this Nanocolloquium, and perhaps it will be an appropriate way to close the series for 2018. So without further ado, I'm very happy to present Gökhan Ünel to you.
Well, thank you very much for this nice introduction. Actually, it didn't make me feel old. Thank you. Forever young, I hope. So, you have read, I guess, the abstract, and you understand the joke about finding the bottom. Our field, high energy physics, particle physics, is about this search. How deep is the bottom? This is a map of the things that we study. Here are the large objects. Here are the small objects. You guys are mostly here, right? You are here, nanoscale. We try to go further down, maybe at femtometers or smaller. That kind of study in the past taught us a lot of things. And especially, we now we came to the understanding of the universe and how it started. Basically, studying smaller and smaller objects and higher and higher energies takes us to the first moments of the creation, the Big Bang. But to reach there, we had to travel a long distance. First, we had to understand the daily objects and then smaller and smaller. Such study, of course, has started long time ago. Man asked this question about the constituents of the objects long time ago. And this gentleman, what they call a pre-Socrates philosopher, Democritus, laughing philosopher, because he was laughing at everything, apparently. He suggested one of the very basic postulates of our field. He said everything else is convention, only atoms and void are existing really. Further studies, of course, took us to the periodical table of elements, and this is well established. But then, in the last years or so, last, say, 150 years, we tried to decipher what's inside the atom, what's inside the elements, and we discovered first the nucleus, and then what was inside it. And then now we are at this scale, we are trying to understand what are the quarks. Now we are down to 10 to minus 16 centimeter or less. Now we are trying to understand whether the quarks have inner constituents like the other objects that we thought they were indivisible, like the atoms here. Maybe the chain will continue. Maybe we will find further deeper constituents, maybe not. For example, the electron has been around since the end of the 19th century, and we still believe it's an elementary particle. In the historical evolution of things, of course, we first handled the matter that we knew. We handled protons and neutrons and electrons. And then, when we were either looking at things that were coming from the sky, cosmic rays, or when we were looking at the collisions in the lab, we started finding interesting particles, bizarre particles. For example, we found positive electrons, we found heavy electrons, we found chargeless electrons, and lots of other objects. Of course, at that point, the particle physics had become a zoo, and some classification was needed. And we came up with this, what we call the periodical table of the 21st century. Okay, this is in Turkish, because I made it in Turkish. I made this one because I'm not happy with the ones which are floating around. I'll tell you why. Okay, here is the electron that we know. Here it's a neutrino, and here are the up and down quarks which are forming the protons and neutrons. The first column, as we call it, the first family, makes up the objects that we see in the periodical table. All the nuclei, and you add enough electrons, you obtain all the atoms. The others, the heavier cousins, heavier brothers, the second family and the third family, they do exist in the lab or in the collisions that you see with the very high energy cosmic rays. These square-like objects, they are of the fermion type. They are the fermions. They obey Fermi-Dirac statistics. These are the basic constituents of the matter. The particle physics, as we will see in a few slides, tries to understand the interaction between different particles. And the interactions are carried with other particles of different statistical behavior. These are, with the cylinders this time, different statistics particles, Bose-Einstein statistics. They are the force carriers. And the latest discovery in this field was the Higgs boson that I will talk about in a few minutes. All these things were achieved using particle accelerators, a field that is relatively new, especially in Turkey. Therefore, I wanted to spend a few slides on that. Maybe this one works, and I will use it. Yeah? No?
I think unipolar is really hard.
Okay, it does. Of course, this gentleman had already figured out that by simply using some objects, you can attract smaller dust-like particles very, very early, about 600 BC. However, during the Dark Ages, nothing was done in this particular area until this date, 1746, in the Versailles Palace. you usually associate Versailles with Marie Antoinette, maybe with lavish lifestyle, etc. However, it turns out in Versailles, there were also saloons in which physics experiments were conducted to entertain the nobility. Nobility of the time was not only playing cards and throwing dice, but they were also interested in these bizarre events of the day. For example, this gentleman, Abbot Nollet, who was the teacher of Lavoisier, in fact, who was beheaded right after the French Revolution. He made this interesting experiment, what I call a fixed target experiment, if you are familiar with the terminology. You see, in this gravure, we see the abbot, and we see a kid hanging from the ceiling using silk cords. He has this rod invented by this gentleman, and after charging the rod, he is charging this other kid, who is now attracting with his hand these gold leaves. Of course, this is being Versailles. You have to use gold. What else? Apparently, he got curious about this phenomena, and in particular, he wanted to understand the speed of the electricity, how fast electricity can travel. And he made an experiment, what I would call the first linear accelerator. And especially, we know the length of the accelerator, 73 meters, because he, who here visited Versailles Palace? Anyone? Okay, 3 people, 4. Thank you. You know that there is this mirror of glasses. Its length is exactly 73 meters. And what he did, since he was the royal preceptor of the nobility's kids, of course, the kids were protected by soldiers. And since this is the tutors, the soldiers obey the professor. He said, hold each other's hand and align yourselves along the corridor, 73 meters. At that time, the Leyden jars were already invented. He discharged on the first soldier, expecting to see a cry, a shout, something from each soldier. And by measuring the time that each soldier would say, ah! He was expecting to measure the speed of the electricity. Of course, when he connected the circuit, the last guy cried immediately, and then he concluded that 73 meters were not enough. Then he said, well, am I not the abbot? Don't I have the monks in my service? Since these things are not working in the linear way, he made the first circular machine. What did he do? This time, just to elongate the periphery, he also added iron rods. This time, the monks were not holding each other's hand, but they were holding iron rods, say about a meter of length. So he made a circular machine, like you see in this caricature. He electrocuted the first monk, and at the end of the circle, he was expecting to see something out of the last monk, and then he was expecting to measure the speed of electricity. Of course, he found it was infinite, and then decided to give up this experiment. You can say that he wasn't very popular in the ecclesiastic area.
What did you say happened to him eventually?
Eventually, he died. Okay. Of course, you know these things. This is a quick summary. Years passed, and then we had the Crookes tube, discovery of the cathode rays, of course. Röntgen changed this tube a little bit and then discovered the X-rays, which brought him the 1901 Nobel Prize. The same Crookes tube was changed a little bit more, added with more stuff, and then a discovery of the electron and its associated Nobel Prize came later on. The early years of the 20th century saw the rise of the power supplies. When you have a better power supply, you have a better source and you have higher energy. Therefore, you can do a lot of things. This is a Cockcroft-Walton generator. The very first one was invented by these two gentlemen, Cockcroft and Walton, in 1932. 400 kilovolts was enough to break the unbreakable atom, and of course, to get the Nobel Prize. This gentleman, he's not very much known, unfortunately, Widerøe. But I think he is a pioneer of almost everything that we use today. Medical accelerators, power supplies, colliding beams. He was full of ideas. At the age of 21, in his discovery notebook that we used to have all as kids, he proposes this device, a Betatron, to accelerate electrons. It was achieved much, much later. He failed because he didn't have enough strong magnets. However, he manages to get, at the age of 26, the first working Linac with this drawing for his PhD, by the way. In Germany. Although the guy is Norwegian, he studied in Germany. And during the war, he made X-ray machines to understand the welding of the iron or steel plates, how well the welding was. Of course, this made him very popular with the German government of the Second War. However, when the war ended, the others, the winners, were not very happy. He was stripped of his citizenship and everything. So collaborating with the powerful government is nice, but maybe not very nice in the long run, depending on the government, of course. Anyway, so linear machines are not, as we see in the Moncotron example, the linear machines are somehow limited. And we are more, the circular machines somehow are more interesting. We are more interested in those, more efficient maybe, in terms of space. So in the 30s, Lawrence invents cyclotron, this small machine, 5-inch. And then you try to make it bigger and bigger. You end up with this 60-inch machine. Is a big device. As you can see, there is a scaling problem here. Of course, the same scaling problem exists in the linear world as well. Also, everything depends on the particle that you are trying to accelerate. If you are working with a proton machine, protons, as you know, are heavier than the electrons, about 2,000 times. You need such a machine for protons. There was, in those years, in 40s, a competition between Berkeley and Stanford. When the Berkeley guys accelerated protons and published this photo, Stanford people accelerated electrons with this machine, and they published this photo saying, well, we can carry our own accelerator. Can you? Of course, you see people sitting here. In this field as well, smaller is better. We like smaller things. Okay. This is a story that I like a lot. Because everybody likes an underdog, right? We all want the underdog to win because we feel that we are the underdog. I think that's the psychology. I told you about that discussion. But what about colliding machines, colliding two beams? That was also taught. And a race started between the US, Princeton, Stanford team, and EU, Italian, French team. The European team was about 2 years behind. But there was a guy here, Tušek, who was another genius of the time. He's an escapee of the concentration camps. He was shot and etc. He survived the thing and became very famous scientist in this area. Anyway, the Italians named it Anello di Accumulazione, ADA for short. They started late, about 2 years, but they finished early. In '64, in 4 years, they got the two beams colliding inside this about 1 meter, 1.5 meter diameter machine. Electron-Positron collisions for the very first time. How? Yeah, of course, the Americans were successful about a year later. How? Let me read you this. Maybe it is too small for you to read. I telephoned Frascati. Please prepare a small quadrupole magnet of such and such dimension to be inserted in this quasi-straight section of ADA. I will fly tonight, come to the lab tomorrow morning, and bring the machined magnet back to Orsay in 48 hours. Thank you, guys. That is the spirit. That should be the motivation. That should be the modus operandi in our field. I'm sure it is the same in any group as well that aims to be successful in short time. Sometimes you have to sacrifice from your sleep. So this business got bigger and bigger in the last years. So in 55, they built the Bevatron, which was about 6 GeV machine. They have found the anti-proton. They got their Nobel. In 60s, in Brookhaven, they built a bigger machine yet, and they got their 3 Nobel Prizes. In 82, CERN constructed the SP P-S, discovered W and Z. They got the Nobel Prize. In 87, Tevatron discovered the top. But this time, although the experiments were quoted, the theoreticians who proposed the top quark received the Nobel Prize. The same thing for Higgs. This accelerator now is here, and the bigger circle is the Large Hadron Collider. Of course, when the Higgs was discovered, the Nobel Prize went to Higgs, although the experiments were quoted again. So I keep saying about CERN. This is a short introduction about CERN now. It was founded right after the Second World War, which was very much devastating for Europe. All the leading scientists had escaped to Americas, and they were trying to regain the knowledge. And they said, well, science for peace. It was established by, by some 12 European states, especially France and Germany, which were at war like 10 years before this establishment. Today it has 23 members, lots of employees, lots of users like myself. Although I am 100% at CERN, my salary comes from US. Some 70 plus countries are represented. We have a budget about 1.1 billion Swiss francs. Swiss franc is very similar to US dollars. So if you want to convert to Turkish money, you know what to do. Work done at CERN yielded 3 different Nobel Prizes: the discovery of W and Z, particle detector development, although it was done in 60s by George Charpak, the Nobel Committee recognized the work some 30 years later. And Charpak, in his Nobel lecture, he said, well, if you had given me the Nobel Prize 30 years ago, I would tell you about its physics. Right now, I'm too old, I don't remember anything. And he discussed completely different things. So, stay young, don't die. If you ask what is Turkey doing in this family, it's here, associated member state. What does it mean? It means you don't have the right to vote. That's what it means. So these are the countries with the users. Some of them are observers, as you see in this year, 2014, Turkey was observer. Some of them are given here as other countries. For example, South Africa is participating to the research at CERN. And as you can see, the African continent is a bit empty. So what do we aim for? What are our goals? We try to push the limits of knowledge, and we ask very basic questions like, how deep is the bottom? How did the universe begin? How did it evolve? What are the particles that constitute the matter, and how do they interact? To answer these questions, as you have seen in the previous slides, we need the equipment that we cannot buy from the supermarket. Therefore, we build our own devices, such as the accelerators and detectors. And that kind of knowledge, unfortunately, is not taught at the university. So we have to educate our own engineers and technicians, and this is a big task. That yielded recently a number of offsprings that we can discuss, such as the World Wide Web, as you know, is coming from CERN. And in the medicine, we have had successes with treatment and diagnosis tools, such as PET, etc. And of course, the idea here is to bring different cultures and countries together. During the Cold War, CERN was the only place where the American and Soviet scientists were working together. We have a number of areas of expertise. For example, we know a little bit about superconductivity. We have achieved 13 kiloamps passing through wires to get very high magnetic field. We work at very high vacuum, like 10 to minus 13. Cryogenics, I will discuss this, is also needed to achieve superconductivity. Of course, we work with magnets. We work with detectors, and it's electronics, rod-hard electronics if needed. And also, we do a lot of data processing. Who works in this area, if you ask? The answer is, well, almost all ages, but mostly about 26. They are PhD students. They do most of the work. And then slowly, number of people and ages, they decay, and we fade away.
What is the measure of work here?
The users.
Number of users.
Number of users, yeah. There was a particular study that was to understand where the people continue their career after leaving CERN. And we found out that a large number of them, as you see in this pie chart, about 55, 60%, they go to industry. Like 30%, they go to the universities and research centers. And there is this other. I don't know what the other is. And when you ask, when people, after getting their PhD, what do they do in the industry? Most of them, they go to computing. Finance as well, because it requires a lot of analysis, a lot of prediction, which is also needed in particle physics. I was also offered a job in Wall Street, by the way, which I refused. No, come on. So this is the CERN Accelerator complex. You have seen this in the previous slides, but this is just to tell you that we don't have a single accelerator, we have a multitude of accelerators. We have linear machines, LINAC. We have circular machines like proton, synchrotron, and SPS and LHC. Why we have so many accelerators? First of all, they were built in time, and secondly, you can change the magnet's current from 0 to whatever it is, 13 kiloamps. The magnets would allow you to change between a finite range. Therefore, like the gears of a car, you need to have a multitude of accelerators. That means you cannot simply accelerate from 0 to LHC energies. You have to have the intermediate machines. Lhc tunnel looks like this. You can see its curvature. It's about 100 meters underground. We are using this niobium titanium superconductor magnets. Superconductivity for these magnets is reached down at 1.9 Kelvin. As you know, 1.9 Kelvin is smaller than 2.73. 2.73 is cosmic microwave background radiation. So these magnets are cooler than outer space. This is achieved using superfluid helium. Therefore, pumps are very important for us. When pumps fail, as it happened in 2008, cooling fails. When cooling fails, the stored energy in these 11-ton magnets is released, and the magnets, they jump, as it happened back in those days. So, okay, we have these interesting facts. Maybe I should simply say that we are the hottest place on, not only on Earth, maybe in this solar system as well, since the lead collisions, the plumb ion collisions, produce heat, what is this? 100,000 times more than the heat at the center of the sun. I discussed that we are coolest. We are also the emptiest. 10 to the minus 13 atmosphere is about the same vacuum level as the interstellar space, not interplanetary, interstellar space. So on the LHC accelerator, we have a number of big experiments, general purpose ones, CMS and ATLAS. I am myself from ATLAS. There are also two dedicated experiments, LHC-B to understand the B quarks and ALICE to understand the heavy ion collisions. ATLAS is something like this. It's about 100 meters underground. The collisions occur at the very center of this device. It's a big device. It's one of the biggest man-made devices. The cavern is dug by man. It's the biggest cavern, man-made biggest cavern. So from here to here is about 25 meters, and from here to here is about 46 meters. The whole device weighs something like 7,000 tons. I am sure you are all familiar with this photo. It was famous. It has even become a backdrop scene for an opera. Anyway. There is this gentleman here for you to compare the size. So how do we detect particles, if you ask? How do you see what you claim to see? Different detectors behave differently for different particles. What does it mean? If you have a photon inside the tracker, it doesn't leave any track. However, it yields its energy inside the calorimeter. If you have, for example, a charged particle, because of the magnetic field, it will bend either this way or that way. Then you would understand its charge, since you know your field. Other particles, such as protons and neutrons, they give their energy, they deposit their energy in this other part of the calorimeter called the hadronic calorimeter. This particular type of particle, muons, they don't interact much except in the outside detectors, which are the muon detectors. And then if you have a neutrino, it leaves no track, is like a ghost, goes away, and you do your checks and sums, meaning a momentum balance. And then you say there is some missing momentum. There must be a neutrino passing by. Okay, we know these. We have the four forces. At least gravity we are very familiar with. It's holding everything together. We are also familiar with electromagnetic force, responsible for chemistry and our cell phones and everything. Weak force is responsible for radioactivity and all the interactions at the center of the stars. Strong force is holding protons and neutrons together, and the quarks inside the protons and neutrons. Since this is the field of particle physics, each force is associated with its particle. Gravity is associated with graviton. We say two particles, they attract each other by the exchange of a graviton. Unfortunately, this graviton is not yet discovered. However, we know that electromagnetism is nothing but exchange of photons, which is very well known. Similarly, weak and strong forces are achieved using by exchanging W's and Z's and gluons. Here are all the particles. Neutrinos here, electron family here, down-type quark family here, and up-type quark family here. As you see, the weak force, by its color of the arrow, the weak force interacts with all of these. The electromagnetic force interacts with these three kind only. And the strong force interacts with these two only. Maybe there is a symmetry and we can deduce something from it. I don't know. Something to be thought about. All these things are put together under the umbrella of the standard model. Electromagnetism and weak force can be written as a single theory that we call the Electroweak Theory. Since Z and Z particle and the photons are very similar to each other except the mass issue. And the strong force, also referred as the quantum chromodynamics, explains the other part. So I'll put everything together. Add the Higgs field, as you see, then you have the standard model. Then to this melange, add the Einstein's gravity, and you almost describe the universe in which we live. So I keep saying Higgs and that. Let's discuss about this a little bit. Higgs in his paper in 64, described a particular field which would give mass to all fermions, plus would explain us why Z and the photon were similar yet different with respect to their masses. Higgs here is alone, and the theory is called by his name because he did something very, very important. He didn't only propose a beautifully good theory, he also proposed an experimental verification. He said, this field is going to create its own particle. Although I don't know its mass, it should be there, search for it. The other guys, these 5 people, these 3 together and these 2 together, they also published similar things, similar theory, but they had never discussed the experimental implications. So my younger friends, physics is an experimental science. Think about the experimental verification of your beautiful theory all the time. We did the experiment for a long, long time, 50 years. Yes?
Was Higgs described in a single paper or a series of papers?
Single. He doesn't like to publish.
I heard his remark that if he were young now, he wouldn't be able to keep his job in the academia.
In an interview, he said, well, I publish whenever I have something important to say. And at the university, they were really fed up with him, and they were asking, how many papers did you write this year? And he was always replying with the same number, 0. And they were thinking to fire him, actually. And they only kept him in the department because one day he might win the Nobel Prize.
Do you know how many papers he has published?
Oh, no, I don't know that. So this Higgs mechanism, how does it work? This question was asked a long time ago by British politicians with a prize, and this series of caricatures were the winner. So this is supposedly as simple as the level of the politicians to understand. I don't know. I guess that depends on the country. Anyway, so how do particles acquire mass? The world, the universe, is like the Higgs field. It's like this room full of people. An important person, let's start with this. An unknown person comes in. Nobody knows him. He's not very sociable. He walks and passes through people. Very easy. Very easy to walk from one end to the other end of the room. This is a massless particle, or quasi-massless. And an important person comes in. I don't know. Einstein comes in, Atatürk comes in. And then people want to talk to him all the time. They gather around him, they say, I have this problem, or could you help me in that? So it is very difficult for him to move from one end to the other end of the room. So this is an example of a massive particle. More interaction with the field brings more mass. He slows down. Now, how does the field itself create a particle? How does the Higgs particles creation work? Somebody starts a rumor. You know? Van Gogh is going to come. Van Gogh is coming. I love his, that. So people gather around and they start gossiping. This is how gossip advances from this corner of the room to the other corner of the room. This is example of the Higgs particles self-creation. So I guess that's it. So how do we search for such an important particle? Of course, standard model helps us a lot. Higgs theory helps us a lot. We know the creation mode. So what happens? 2 protons, for example, collide. Proton, antiproton, doesn't matter. For example, we have 2 gluons coming from each quark. They interact together, for example, through a top quark. And then, since top quark is the heaviest of the quarks, it has to interact a lot because of the previous discussion with the Higgs field, creating the Higgs particle. And then, from the theory, Higgs theory, we know how this Higgs particle would decay. Well, depending on its mass, it can decay to this, it can decay to that. Therefore, spanning its mass, we have to search for all possible decay channels. One of the easiest ones, Higgs decaying to a Z and a Z star in their turn, which would decay to two charged leptons, yielding four lepton final states. You do your experiment, you collide lots of protons, you observe. You also compare this with the prediction coming from the standard model, because there are non-Higgs processes which would emulate this four lepton final state. And then you compare your data with your theory. You either see the particle or you don't. Let's see how the accumulated data was compared to the calculation from standard model. As you see, there is this region here where some number of data are collected. Here is number of events, but the theory wasn't predicting that many. Of course, here the theory is standard model without the Higgs. Since we didn't know the mass of the Higgs, we had to estimate and measure from this work. Today we know, with more data, that Higgs sits at 126 GeV. Okay, so now you see this, now we understand how things work, more or less. There is the Higgs boson interacting with these. If you want to, for example, observe the Higgs boson's decay to two photons, how do? You have the Higgs interact with one of the quarks, and then the quarks interact with photon, and then you say, I have seen the Higgs decay to two photons, for example. After all that discussion, by the way, I should say this, LHC, at the end of this year, 2018, LHC stopped. It is going to restart in 21. We have about 2 years to improve the machine and to improve the detectors. We need, obviously, because you have seen the graph, we need more statistics. To get more statistics, we need to improve the accelerator. When more events come in, we need a better detector to measure. So upgrade time, 2 years upgrade time. Anyway. So you can ask, is this the real bottom? Do we understand now? Well, it depends, is the answer. Why? Because you look at this and you say Earth is flat. But if you move away and look again, you figure out that Earth is in fact not flat, round. So sometimes things depend on your point of view. And to change our point of view, although standard model agrees with the experiments to an astonishing level of precision, you ask few things. For example, are we sure that the quarks and the leptons that we have seen today are the fundamental particles? Well, we don't know. We have seen that the fermions are the matter particles and the bosons are the force carriers. Is there some sort of symmetry or asymmetry in the words of Big Bang theory? Maybe, maybe not. Why there are really 4 forces? Maybe 3 if you consider electroweak theory. Why this number? It is strange. And also, everything seems to be happening in 3+1 dimensions. That's also interesting. Why? We have a number of measurements, not coming from colliders, but observations in the sky, dark matter and dark energy, cosmology's contribution. And we haven't produced these things in the lab to study, so we don't know. To really study and understand, we need to be able to experiment on those. Observation is not enough. So if the standard model is not the real bottom, what is the bottom? So in other words, if we can manage to go beyond the standard model, what shall we find? Well, there are a number of candidate theories. I will discuss only 2 of those. An exciting theory is what we call the extra dimensions. And the question that gives extra dimensions as the answer is this. The gravity is much, much, much weaker than the other forces, 10 to 40 times weaker than the other forces. Why? Why? Some clever people suggested that maybe we are living in a universe with more dimensions. And in our poor world, poor sheet of 3 plus 1, we only see a dim shadow of the gravity. That's why it is so weak. How could that be? Well, say we are living here. This is my 5-dimensional world. The 5th dimension, represented by this y, is the extra dimension that I cannot observe. And over here, when this extra dimension, in this extra dimension's origin, in the Planck sheet, in the Planck scale, gravity is as strong as the other forces. But I am here, living here in the TeV sheet, very far away from the origin. And the metric that takes me from here to here decays exponentially. That explains why I observe the gravity so weakly. This is the shadow that I'm talking about. Then you might ask this question. If there are additional dimensions, how come I don't see them? How come we didn't discover them up until now?
Another question.
Sorry for that.
Why not for the electromagnetic force? I mean, weak, strong, you could say range is finite, but electromagnetic is also infinite. Why wouldn't it be affected by the same way as gravity, like this extra dimension?
Let me understand a little bit better. You are asking whether electromagnetic force would also exist in multidimensional world. Is that so?
Yeah, I mean, we're trying to explain why gravity is so much weaker than the other forces, saying that gravity is actually equally strong as the others in this, if you included this 5th or 4th dimension, whatever. And you could, I guess, you could get away by saying, why wouldn't the other forces also get strengthened by saying that weak and strong forces have finite range. But I wouldn't buy this in the case of electromagnetic force. As far as we can tell from cosmology, the way electromagnetic force behaves is the same in this scale and the same scale as the galaxy. So wouldn't electromagnetic force be proportional to also stronger and still be ahead of gravity at this Planck sheet? That's the Planck sheet.
My question was very similar as well. So I will ask, so you answer both. Also, the question is same actually, why the other forces are not affecting from this, but maybe from the light aspect. Light is getting bent from also the gravity. So they are in very close interaction. I think this is suggesting that electromagnetic force can be affected.
You see, electromagnetic force, light, is affected by the world, by the universe in which we live. The change here in the extra dimension is so deep, and the strength it carries is that we change the universe or the way that we perceive the universe. There are, of course, variations of the extra dimension theory that I am not going to mention here, in which the electromagnetic force and the weak particles as well can go to extra dimensions, and they also can travel up. But this is the simplest possible extra dimension variation that explains the weakness of the gravity. You could also have theories, as I said, in which electromagnetism could go up to this Planck scale. But that doesn't solve the problem. It doesn't help you. It doesn't help you with this problem that I have posed, the very first line. Remember, we are trying to solve this question. Then, starting with that, you can have variations as much as you want. You'll remember that the very first extra-dimensional model was proposed by Kaluza and Klein, which was unifying, in fact, electromagnetism and gravity in an extra dimension which was exactly like this. Maybe electromagnetism and gravity are coupled. I don't know. I guess nobody knows. It's an open question. Of course, maybe. You understand this explanation, right? If you are this guy walking on a rope, for you, there is no direction but forward and backward. Also, if you are skillful, you can jump up. Well, if you go down, it's a bit difficult if this is high enough. But if you are this little bug here, you have one extra dimension, right? You can go around the rope. That means if you look deep with higher and higher energy, maybe we will be able to discover an extra dimension like this. This we call a closed extra dimension. Because if you are this bug and you start walking, you end up in the same place. This, however, is an open extra dimension. You go from here to here. There are variations in every theory. Okay. This is another candidate that we particularly like. It says grand unified theory. What does it mean? When you measure, for example, the charge of an electron, you discover that you go closer to the electron, and since it polarizes the vacuum polarization effect, quantum field theory, its charge changes, its mass changes. In the quantum field theory, we call this the running mass and running charge. When you run the coupling constant, that means if you consider its value at higher and higher energies, you discover that the strength of the three forces, strong, electromagnetic, and weak, they seem to be unifying at around this 10 to 16 GeV range. That is an interesting phenomenon. And people think that this could be an explanation, there could be an explanation for this effect, and maybe the standard model and the group structure of the standard model is in fact going to show us that there is a bigger, larger group, a symmetric group, just like this exceptional Lie group E6, which will encompass the existing group structure of the standard model, which is SU3 cross SU2 cross U1. And this particular grand unified theory, E6, is interesting for me because it was proposed by this gentleman, Feza Gürsey, from around here, actually. If these forces unify, there is an easy implication that you can guess. If they unify, that means they interact with the particles that they were not interacting here. Here, weak force is different than electromagnetism. Here, they are the same. So everything interacts with everything else. That means new interactions and new particles are predicted. In this model as well, new quarks and new leptons are predicted. And what we did with my student Berare here, was to search for new quarks predicted by this model. We call it beyond the standard model quark search. We named these quarks uppercase D, and we looked for these in the LHC data. How did we do this? We know from the theory how these quarks would decay if they do really exist in the nature. And we search for these final states. What means to search? Basically, you come up with an algorithm that would try to figure out if these can be picked from the collisions that you recorded. There is something that I want to mention here. Of course, you thought of writing a computer code to achieve this. But then you write once, you write twice, it becomes rather boring. And instead of writing code like this in Python or C++, we invented a language that we call the CAT-LANG, Particle Physics Analysis Description Language, CAT-based, human readable. In this language, instead of writing a code like this, rather cryptic if you use C++, you write things like number of leptons should be equal to 2 or greater than this, number of jets, add this particle and that. The computer understands this, interprets at runtime, and then gives you the answer. A little bit like in Star Trek, computer, analyze this. If you are interested in this, there is a published paper, and then we are organizing a workshop in the coming year at Fermilab. So, if all these studies do not give us the real bottom, what is the plan B? Well, the plan B is to build a bigger accelerator, maybe bigger. You'll see. There are options. For example, you can build a linear machine. CLIC stands for Compact Linear Collider. It is so compact that the length in the smallest possible option is 11 kilometers. And the largest option, depending on its energy, it's 50 kilometers. So it is not yet totally compact. This is maybe going to be built. I don't know. But it proposes something very interesting. Normally, in LHC, when the protons travel about a meter, they gain something like 5 million volts. This value in superconductor machines is like 40 million volts. In the CLIC technology, they had originally proposed this number to be 100. But then they started doing the experiments, and the accelerating structures were not good enough. They were sparking. Now they are talking about 75. Obtaining 75 million volts per meter reduces the size of the accelerator drastically. That's why it was called compact. This is.
Just to be clear, what does compact mean here?
Well, here compact means these days 11 kilometers. Yeah. But this is a discovery machine, E plus E minus linear collider. If you want to build a machine dedicated, for example, to search the properties of the Higgs, then you can build an ILC, International Linear Collider, with its new name. You can just build it with the conventional technologies. You don't need to use this one. And then it will be like 30 kilometers, but it will give you exactly all the information that you need from Higgs. And if you decide to build it in Japan, they are going to cover 50% of the cost. What is this? So you might also say, I don't want to build a new machine. I want to use the existing machines. I want to economize on money. Then you have the Large Hadron Collider already. And then what you can do, you can build an electron machine to hit the protons with the electron. You can do deep and elastic scattering. This is called Large Hadron Electron Collider. The Turkish teams from here, in fact from Ankara, are contributing to this. However, there are a number of options for the electron machine. Initially, it was proposed to build the electron machine inside the Lhc tunnel, but that's maybe a dream. You can also build an electron machine like this, or you can build a circulating Linac like this. There are options, and people are studying.
Can I have some?
Sure.
So we said that the forces acts like the same force in certain energy, like the big energies.
Mm-hmm.
How close are we to that energy, like percentage?
Oh, we are far away from that. You see, this is in GeV. We are here. We are at 13 TeV. This is what, 10 to minus 4, right? We are here. That is here, 10 to 16.
So we are far from away from proving those extra.
But wait a moment. These can happen at different scales. Maybe 10 to 18, maybe 10 to 16, maybe early. We don't know. We are guessing that there is a large group like E6, which would exist in these energies. But then we don't know at what level it breaks down. Okay? The breaking down of the large group can happen at the lower energies, such that we see the implications, such as these new particles. Since we don't know at what level this symmetry breaking occurs, we don't know the masses of the new particles. Therefore, we have to search at the higher and higher energies, just like we didn't know the mass of the Higgs. Okay, forward. So there is discussion about building yet another big machine. Here now is the LHC ring. And here is the proposed future circular collider, which is much, much bigger, like 100 kilometer long. This is the Salem Mountain for those who know about it. This is supposed to be a 100 TeV machine, taking the energy scale 10 times up. Now we are at 13 TeV. People are discussing about this, whether it could be a proton-proton machine, electron-proton, or both. That is possibility. The Chinese have copied this, and they are proposing a circular electron-positron. Oh, I hope I didn't do a social faux pas. Anyway, they are interested in building an electron-positron machine, one-to-one copy of the FCC electron.
Just to have an idea,
Sure.
what does a new accelerator cost nowadays?
Oof. If you are...
I find that Japanese are paying the 50% off.
But that's a linear machine.
Oh, so cheap.
Well, everything is relative. Cheap for you. You see, for building a linear machine, you can start from scratch. If you are going to build such a circular machine, you cannot start from scratch. You have to have the infrastructure. You cannot build a machine with a car with the 6 gear only. You have to build 1, 2, 3, 4, 5 as well. Therefore, this is a circular machine like this can only be done at CERN, nowhere else. Nobody else can shoulder the cost. Like this will be hundreds of millions, billions.
How about a linear one?
Linear one, I think it's written here. No, just the technical properties. This will be like,
10 million?
no, less hundreds.
Hundreds?
Mm.
Oh, billion.
Hundreds of millions of dollars.
That's nothing.
That's nothing. Well, as I said, it depends. Who pays? If CERN pays, it is a lot.
But it's over many, many years and hopefully contributed by at least a dozen countries.
CERN budget is fixed. Whether you do fantastic publicity or not, you will get the same money. Even if you don't discover anything, you will get the same money. CERN budget is fixed. And by the way, for a comparison, CERN budget is covering people, electricity, heating, research, all the purchases, everything, 1.1 billion Swiss francs. Nestle, the biscuit or the baby food you are buying for your kid maybe, research budget, how much do you think it is? More than that. 1.5 billion Swiss francs. What did they invent? I once asked this.
Biscuits.
Well, maybe you have been to a movie theater, you have seen these biscuits, 2 biscuits, and in between ice glasses, ice cream in between. So you can eat ice cream without getting your hands dirty because there are the biscuits on the side. Fantastic invention. Okay.
But you cannot bite a quark.
You can only interact with electrons, as you know, at the EV level. Anyway, apart from joking, we have discussed what can be done with the conventional technologies. What are then the emerging technologies? You can ask this question. And I'm giving you just 2 examples, and this will be my last slide. There is this thing now, popular thing called Wakefield Acceleration. The idea is this. You produce a plasma by heating a gas, for example, with your microwave oven. And then inside this plasma, you shoot either another beam, like protons, or a powerful laser. And when the ions are pushed forward, they leave a trace behind, their wake field. Like a boat which is traveling and leaving its wake field behind. And then you push in, an ion channel, as it says here, opens, and you push in your secondary beam, for example, your electrons. The large number of ions which are moving in this direction, they pull now the electrons which were sent later on. So these guys, sorry?
Via the electromagnetic force.
Yes, yes. So you basically, you have pushed these ions somehow, laser or proton beam. Now they are pulling these electrons behind them using their wake field. There is this awake experiment at CERN and Bella experiment at Berkeley. They have tested this. CERN doubled the energy of the electron beam. And Berkeley, they managed to get like 2 GeV at 9 centimeters. That's fantastic compared to the previous technologies. However, since this is emerging technology, there are two problems. The number of particles you push in today is very small. Number two, the energy dispersion is big. So you can't single out particles to use in your collider. So the second option.
Let me also make a quick comment. I visited this lab at Berkeley where this experiment was done.
Mm-hmm.
So it's centimeters, but to run it, actually, the guy has lasers occupying 2 floors.
Well, that is your area. You should have intervened. Anyway, now another possibility with a laser now. Assume you have this silicon with a channel. You push in your already at the speed of light electron beam. What happens? And then you also fire a laser in the perpendicular direction. The electric field then fits inside this geometrical structure and is like this. Because of the electric field's changing direction, if you don't build these holes, your electron is going to be affected by the field in the direction that you want, and in the next phase is going to be reversed and slowed down. Therefore, you open these channels to make the amplitude of the electric field go down. Here, the amplitude is large. Here, the amplitude is very much reduced because of these channels. So, you also synchronize your laser with your electron beam. Over here, your electron accelerates. Here, it decelerates, but a little bit. So, I call this the Yenicheri effect. Like the Janissaries who are walking 2 steps forward and 1 step backward, the electron accelerates a lot, decelerates a little bit, then accelerates a lot. That's fantastic idea. They call it accelerator on a chip. And they managed to make the demonstration unit work at Stanford, and they obtained something like 300 MeV per meter. That is fantastic. And basically, you can see how big the accelerator is on the tip of a finger. So as I said, this is my last slide. The search for the bottom continues just like the search for the golden fleece of the Argonauts. Well, thank you.
Thank you for the inspiring talk. Any questions? Comments?
Well, that's excellent.
More specifically? Maybe I'll have a specific comment. It's just not
Please.
idea to throw around. You know, we talked whether there might be a connection between electromagnetic fields and gravity, and
Mm-hmm.
there's actual reason to think so, because in quantum theory there is an elephant in the room, which is eerily reminiscent of black matter radiation before the discovery of quantum mechanics, namely that there is vacuum energy. You know, according to quantum mechanics, there is always some vacuum field. And this is very real. If you build lasers like I do, every parametric laser starts from vacuum fluctuations. It's very, very experimentally accessible. And according to theory, this vacuum field goes up to infinity in frequency. Even if you add up its energy, it goes and becomes infinite. So people get away by saying that, okay, it's only a fixed energy like a DC state, it doesn't change anything. Except when you look into general relativity, where the bending or the gravitational tensor depends on the total energy, not the relative energy. So there is a clear inconsistency with current general relativity and current quantum field theory.
Yes.
Probably then there is a connection that might be a key to finding a solution.
Something to be understood, yeah.
Here's a question.
What was the purpose of the fields where you do deceleration again?
Well, I wish I could eliminate those fields, but since I cannot eliminate, I try to weaken them. This is just like the RF field. It changes direction very rapidly, right? And you only want one side. You only want the side that you can use. The other one you cannot use. You want to eliminate it, and the method of opening the channels here weakens its amplitude. Sure.
So we know that the forces act like the same force in higher energy levels. Can we say that in the beginning of the universe there was like only one force and that they...
That is our holy grail, of course. Yes, that's the idea. At the beginning of the universe, when the energy concentration was very high, there was only one force. Yes, that theory of everything. That's what we are trying to achieve. But then, even if we come up with a grand unified theory, gravity is left out. Gravity is not included. Why? Because in the particle world, gravity is meaningless. We never discuss the effects of the gravity except when we do Millikan experiment in graduate school, I guess. Why? The particles are so light, so small. Gravity has no meaning. Gravity gains meaning when we consider bigger and bigger objects, or when we go to very heavy, close to very heavy objects like black holes. Also, gravity could gain any meaning if we have, for example, these extra dimensions. Another implication of the proposed extra dimensions is the possibility of enlarging the Schwarzschild radius, and therefore open the possibility of creating micro black holes inside the accelerators. That would be something fantastic if we observe a micro black hole. It would tell us lots of things. Yes, yes. Apart from that, gravity is not considered much. Well, it is considered if you want to build a decent accelerator, because the accelerator is buried underground. It feels the effect of gravity. Pool of the moon, even the amount of rain changes its behavior. Other than that, gravity, it's not so grave.
One more question.
You mentioned there might be additional dimensions that we can't sense.
Yes.
Right?
Yes.
And they can form like very tiny loops.
Yes.
If I'm not mistaken.
Yes.
But the three dimensions, the spatial dimensions that we can sense, is it possible that they just form very large loops, but they just look linear and infinite? Possible?
Something that I have not considered. Let me think. We are still receiving. Okay. No is the answer. I discussed inside. No. Why? I'll tell you. Because of Hubble constant, we know that the universe was changing the Hubble constant. We know that the universe was a point at the very beginning at Big Bang. And we know that it is still expanding. And we know that the acceleration, the expansion has acceleration, positive acceleration. So the universe is going to go bigger and bigger. Therefore, since I cannot see the edge of the universe, and I know that it is going to be expanding with acceleration, the special dimensions cannot go over and loop. That's not possible. You understand what I'm saying?
Yes.
Okay.
But doesn't the universe acts like a closed space? Like when you go over one place, you come out with like a Pac-Man. You come out of the screen and then come out other side of the screen.
Is that science fiction?
No.
No, it's not like that. It's not like
So
Pac-Man.
is there an age of the universe?
Is that?
Is there an age of the
Yes, there is an age of the universe. 13.7 billion years. Age. Ah.
Finite limit science.
Huh?
Finite science, he's asking.
Yes, the answer is yes, and it is related to the age of the universe. We know how old the universe is, and we know how fast the expansion of the universe was. Therefore, I can calculate. It is very big, but it is finite. It is infinitely big, but it is finite.
But isn't the space, when the universe expands, it expands also the space. So there's nothing else outside of the universe.
Yes. So?
So there's no little edge. Like when you go to the end of the universe, you don't see like an edge or an end. You just see the rest of the universe from there. So it's actually a loop.
But you are talking about only on our universe. It's our universe. Then you have new universes. I think you are talking about this, right?
No, I don't think he's talking about multiverse. He's saying, if I understand correctly, if I stand at the very edge of the universe and I look back, I would see the other end. He says something like that.
I'm saying you don't see an end.
Yes, but that doesn't necessarily mean that you can circle around and come from the other direction, right?
I'm just saying the space is like the universe expands the space, so there's nothing outside of the universe.
Okay, we are not contesting that.
So when you travel around the Earth, when you come to the same point, when you go to the edge of the universe, you will actually come back to the other side of the universe. Like it's connected. Doesn't make any sense.
We are considering like the edge of a sphere, and you want to walk over the sphere. Is that what you are saying? Okay, I understand what you mean now. In that respect, I understand, yes. The expansion is supposed to be like a circular object, yeah. I was thinking of traveling in the diagonal direction, not in the periphery.
Okay, maybe we should wrap it up here, and we'll have Gökhan here to discuss this further. So let's thank him one more time for this great talk.
Thank you for listening.